Two adjacent service drops with separate meter mains create a potential for electrical shock if the drops come into contact. If one of the drops fails, it could ignite the other, creating a fire hazard. The National Electrical Code and the Canadian Electrical Code do not allow two separate service drops with adjacent meter mains. Bonding and grounding must be properly designed to prevent electrical shock and fire hazards. It is questionable how this can be achieved with two separate service drops. As an inspector, one is responsible for ensuring that electrical installations meet code requirements and are safe. If one signs off on an unsafe installation, one could be liable for any resulting damages. It is unethical to approve an installation that one knows to be hazardous. The inspector may not be fully aware of the potential hazards associated with this type of installation. One should contact the utility company and explain the situation. They may have specific requirements or guidelines regarding multiple service drops. If the utility company insists on connecting the drops, one should document one's concerns and refuse to sign off on the installation. The utility company may connect the drops if they have reviewed the installation and determined that it meets their specific requirements and codes. However, it is unlikely that they would connect two separate drops with adjacent meter mains due to the potential hazards described above. Their refusal to sign off on the installation is justified based on the potential hazards and code violations. It is important to prioritize safety and adhere to professional standards, even when faced with objections from senior inspectors. Let's delve deeper into the intricacies of electrical service installations, specifically focusing on the scenario of multiple service drops. The National Electrical Code, a comprehensive set of standards for safe electrical design, installation, and inspection to protect persons and property from hazards arising from the use of electricity, plays a crucial role in ensuring the safety and reliability of electrical systems. When dealing with multiple service drops, several potential issues arise that must be carefully considered. Firstly, the physical proximity of two separate service drops increases the risk of accidental contact between the energized conductors. This contact can lead to a short circuit, resulting in a surge of current that could damage equipment, ignite a fire, or pose a severe electrical shock hazard to anyone in the vicinity. The NEC addresses this concern by specifying minimum clearances between overhead service conductors and between service conductors and other objects. These clearances are designed to prevent accidental contact and ensure that there is sufficient insulation to withstand potential voltage surges. Secondly, the presence of two separate meter mains raises questions about the proper bonding and grounding of the electrical system. Bonding refers to the intentional electrical connection of all metal parts that are likely to become energized, creating a low impedance path for fault current to flow back to the source. Grounding, on the other hand, involves connecting the electrical system to the earth, providing a path for fault current to dissipate safely. In a typical single-service installation, the grounding electrode system, which consists of ground rods, ground plates, or underground metallic water pipes, is connected to the service equipment, providing a common ground reference for the entire electrical system. However, with two separate service drops and meter mains, it becomes more complex to ensure that both systems are properly bonded and grounded together. The NEC requires that all grounding electrodes be bonded together to form a single grounding electrode system. This bonding helps to equalize the potential between different parts of the electrical system, reducing the risk of electrical shock and minimizing the effects of ground faults. The size of the grounding electrode conductor, which is the conductor used to connect the grounding electrode system to the service equipment, is determined by the size of the service entrance conductors. It is essential to select the correct size grounding electrode conductor to ensure that it can safely carry the maximum available fault current. Furthermore, the NEC specifies requirements for the location and installation of grounding electrodes. Ground rods, for example, must be driven at least 8 feet into the ground and must be spaced at least 6 feet apart. Underground metallic water pipes must be in direct contact with the earth for at least 10 feet to be considered a grounding electrode. In addition to bonding and grounding, the NEC also addresses the issue of overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow, which can cause overheating, damage to equipment, and fire hazards. In a multiple service drop installation, it is crucial to ensure that each service drop is properly protected by an overcurrent protection device. The size of the overcurrent protection device must be carefully selected to match the ampacity of the service entrance, conductors, and the connected load. Moreover, the NEC requires that overcurrent protection devices be readily accessible and clearly labeled. This allows for quick identification and isolation of faults, minimizing the risk of electrical hazards. Another important consideration in multiple service drop installations is the coordination of the electrical systems. Coordination refers to the process of selecting and setting overcurrent protection devices to ensure that a fault in one part of the system does not cause the entire system to shut down. In a coordinated system, the overcurrent protection device closest to the fault should trip first, isolating the fault and minimizing the disruption to the rest of the electrical system. Coordination is particularly important in multiple service drop installations, as a fault in one service drop could potentially affect the other service drop. The NEC provides guidance on coordination, including requirements for selective coordination and zone-selective interlocking. Selective coordination involves selecting overcurrent protection devices with time current characteristics that allow the device closest to the fault to trip first, while the upstream devices remain closed. Zone-selective interlocking involves using communication between overcurrent protection devices to allow the device closest to the fault to trip first, while the upstream devices are temporarily blocked from tripping. The use of appropriate wiring methods is also crucial for ensuring the safety and reliability of multiple service drop installations. The NEC specifies various wiring methods, including rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and cable assemblies. The selection of the appropriate wiring method depends on the specific application and the environmental conditions. For example, rigid metal conduit is often used in areas where there is a risk of physical damage to the wiring, while cable assemblies are commonly used in residential applications. The NEC also provides requirements for the installation of wiring methods, including requirements for supporting, securing, and protecting the wiring. Proper installation of wiring methods is essential to prevent damage to the wiring, which can lead to electrical hazards. Furthermore, the NEC addresses the issue of voltage drop. Voltage drop refers to the decrease in voltage along a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of electrical systems, and create safety hazards. The NEC recommends that voltage drop be limited to 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to select conductors with sufficient ampacity and to keep conductor runs as short as possible. In addition to the technical requirements of the NEC, there are also legal and ethical considerations to be taken into account when dealing with multiple service drop installations. As an electrical inspector, one has a professional responsibility to ensure that electrical installations meet code requirements and are safe. If one signs off on an unsafe installation, one could be held liable for any resulting damages. It is unethical to approve an installation that one knows to be hazardous. In conclusion, multiple service drop installations require careful consideration of various technical, legal, and ethical factors. The NEC provides comprehensive guidance on the safe design, installation, and inspection of electrical systems, including multiple service drop installations. By adhering to the requirements of the NEC and exercising sound engineering judgment, it is possible to ensure the safety and reliability of electrical systems. Now let's consider specific challenges with multiple service drops to a single property with two dwellings, such as a main house and a granny flat. The NEC generally permits only one service to building or structure, as stated in NEC 21. There are exceptions, however, outlined in 21A3D. Firstly, separate services are allowed when the capacity requirements exceed the capacity of a single service. This might occur if the total electrical load of both dwellings is substantial. Secondly, separate services are permitted for fire pumps, which require a dedicated and reliable power source. Thirdly, separate services are allowed for emergency, legally required standby, or optional standby systems. These systems need to operate independently of the normal power supply in case of an outage. Fourthly, multiple services are permitted by special permission. This requires the authority having jurisdiction, often the local electrical inspector, to approve the installation based on specific circumstances. These circumstances might include large area buildings, multiple occupancy buildings where each occupancy has its own service, or industrial complexes with specific load requirements. If in the scenario of a main house and a granny flat, it's unlikely that the capacity requirements alone would justify two separate services unless the combined load is unusually high. It's also unlikely that the other exceptions for fire pumps or emergency systems would apply. Therefore, obtaining special permission from the authority having jurisdiction would be essential. The inspector would need to evaluate the entire installation, considering factors such as the size of the dwellings, the expected electrical loads, the available utility infrastructure, and any specific requirements of the utility company. If special permission is granted, the installation must comply with all applicable NEC requirements for multiple services. This includes proper bonding and grounding, overcurrent protection, wiring methods, and coordination. The grounding electrode system must be common to both services, ensuring that all metal parts are bonded together and connected to the earth. Overcurrent protection devices must be properly sized and coordinated to prevent cascading failures. Wiring methods must be appropriate for the environment and installed according to code. In addition, the NEC addresses the issue of service disconnecting means. Each service must have a disconnecting means that can simultaneously disconnect all ungrounded conductors. The disconnecting means must be readily accessible and clearly labeled to indicate which service it controls. The location of the service disconnecting means is also important. The NEC requires that the disconnecting means be located at a readily accessible location either outside the building or structure or inside nearest the point of entrance of the service conductors. This ensures that firefighters and other emergency personnel can quickly disconnect the power in case of a fire or other emergent. Now, let's consider the specific concerns raised about bonding and grounding in the scenario of two separate meter mains feeding the main house and the granny flat. The use of a single ground rod for both services is highly questionable and likely violates the NEC. As mentioned earlier, the NEC requires that all grounding electrodes be bonded together to form a single grounding electrode system. This typically involves connecting multiple ground rods, a ground ring, or an underground metallic water pipe to the service equipment. A single ground rod may not provide sufficient grounding impedance, especially if the soil conditions are poor. The NEC specifies minimum requirements for the resistance to ground of the grounding electrode system. If a single ground rod does not meet these requirements, additional ground rods must be installed. In addition, the size of the grounding electrode conductor must be adequate to carry the maximum available fault current. A small grounding electrode conductor may not be able to safely handle a ground fault, potentially leading to equipment damage or electrical shock. The inspector's concern about proper bonding is also valid. Bonding ensures that all metal parts that are likely to become energized are electrically connected, creating a low impedance path for fault current to flow back to the source. This helps to trip the overcurrent protection device quickly, minimizing the risk of electrical shock. In the scenario of two separate meter mains, it's crucial to ensure that all metal parts of both electrical systems are properly bonded together. This includes metal enclosures, metal conduits, metal water pipes, and any other metal parts that could potentially become energized. The bonding conductors must be properly sized and installed according to the NEC. Furthermore, the bonding connections must be reliable and corrosion resistant. The use of improper bonding techniques or materials can compromise the effectiveness of the bonding system. Therefore, it is critical to carefully inspect all bonding connections to ensure that they are properly made and meet code requirements. The senior inspector's assertion that the utility company will connect both masts with one drop raises additional concerns. While it's possible that the utility company has specific requirements or guidelines regarding multiple service drops, it's unlikely that they would connect two separate drops with adjacent meter mains due to the potential hazards described above. It's essential to verify the utility company's requirements in writing and to ensure that the installation complies with those requirements. If the utility company insists on connecting the drops, it's still the inspector's responsibility to ensure that the installation meets all applicable NEC requirements. The inspector should document his concerns and refuse to sign off on the installation if he believes that it is unsafe or violates the code. Ultimately, the safety of the electrical installation is the inspector's primary concern. He should not compromise his professional integrity or ethical standards to accommodate the homeowner or the senior inspector. It's better to err on the side of caution and refuse to approve an installation that is questionable than to risk the safety of the occupants and the property. Consider a practical example. Suppose a homeowner wants to install an electric vehicle charger in the granny flat. This adds a significant load to the electrical system and could potentially overload one of the services if it's not properly sized. The inspector must carefully evaluate the load calculations for both dwellings to ensure that each service has sufficient capacity to handle the expected load. If the load calculations indicate that one of the services is overloaded, the inspector should require the homeowner to upgrade the service or to install a load management system to prevent overloading. In addition, the inspector should verify that the electric vehicle charger is properly installed and grounded according to the NEC. This includes ensuring that the charger is connected to a dedicated circuit with the appropriate overcurrent protection and that the grounding electrode conductor is properly sized and connected. Another potential issue is the presence of existing electrical wiring in the granny flat. If the wiring is old or damaged, it could pose a safety hazard. The inspector should carefully inspect the existing wiring to ensure that it is in good condition and meets current code requirements. If the wiring is found to be deficient, the inspector should require the homeowner to replace it or to repair it. Finally, it's important to communicate effectively with the homeowner and the senior inspector throughout the inspection process. The inspector should explain his concerns clearly and concisely and should provide specific recommendations for correcting any deficiencies. He should also be willing to listen to the homeowners and the senior inspector's perspectives and to address their concerns. By working collaboratively and maintaining open communication, it's possible to reach a mutually acceptable solution that ensures the safety and reliability of the electrical installation. Remember, the inspector's role is to protect the public from electrical hazards. He should not be intimidated by senior inspectors or pressured by homeowners to compromise his professional standards. He should always prioritize safety and adhere to the code, even when it's difficult or unpopular.